The steel beneath Lieutenant Commander Joseph T. O'Callaghan's boots vibrated with mechanical rhythm. March 19, 1945, found him 50 miles from Honshu's hostile coastline. The Catholic chaplain had risen at 4 in the morning darkness. Mass had been celebrated in the cramped wardroom. Dim lighting cast shadows across bowed heads of early watch sailors. Now Pacific dawn painted the horizon in soft colors. O'Callaghan stood near the towering island superstructure. His eyes followed the urgent movements of ordnance crews. They wrestled massive, tiny Tim rockets toward waiting Corsair fighters. Each weapon stretched 11 feet in length. 500 pounds of high explosive filled every warhead. Enough destructive power to crack battleship armor like an eggshell. These rockets had never tasted combat before this day. Franklin would claim the honor of first launch. The experimental weapons would streak toward Japanese homeland targets. O'Callaghan watched the careful choreography of preparation. Men moved with practiced efficiency around the deadly cargo. What the chaplain could not foresee was approaching catastrophe. 3 hours remained before his ship became a floating inferno. Naval architects had calculated such damage would sink any carrier within minutes. USS Franklin would suffer losses that defied survival statistics. 807 men would die in an instant. More casualties than any American warship had ever absorbed and continued fighting. Her flight deck would transform into an ammunition holocaust. The hangar deck would become a furnace reaching 2,000 degrees Fahrenheit. Yet the sea would not claim her. Against every law of naval warfare, she would endure. Against every expectation of material science, she would survive. The reason lay buried in her construction 5 years earlier. Virginia shipyard workers had built innovations their supervisors called impossible. Morning routine carried the familiar tension of combat operations. Task Force 58 had pounded targets around Kyushu and Honshu for 3 consecutive days. Defenses were being softened before April 1st. The Okinawa invasion approached rapidly. Franklin served with Task Group 58.2 under Rear Admiral Ralph Davison's command. She had moved closer to Japan than any American carrier had dared venture. 50 miles from enemy coastline meant exposure to land-based aircraft. Captain Leslie E. Garris held command since November 1944. He pushed his ship forward with calculated aggression. Crew members whispered concerns about unnecessary risks. They nicknamed him Custer for his bold tactical choices. But mission requirements demanded proximity. Closer operations meant more sorties per day. Aircraft could remain longer over targets. Franklin's first strike had departed at dawn. 12 Corsair fighters and 16 Avenger torpedo bombers roared off the deck. Their destination was airfields surrounding Kobe. The second strike sat spotted on deck awaiting launch orders. 31 aircraft warmed engines in morning air. Propellers turned in steady rhythm. Pilots ran final checks from their cockpits. The flight deck resembled controlled chaos. Every movement followed careful choreography. One mistake meant disaster for everyone. Ordnance men had mounted experimental Tiny Tim rockets on wing pylons. The massive weapons required wrestling into position. Aviation gasoline trucks had completed fuel tank refilling moments earlier. Below in the hangar deck, 22 more aircraft waited their turn. 16 carried full fuel loads. 5 were armed with bombs and rockets for the next launch cycle. This represented the most vulnerable moment in carrier operations. Hundreds of tons of aviation gasoline sat exposed across 2 decks simultaneously. Mountains of ordnance waited in ready positions. A single spark could trigger catastrophe beyond imagination. At 7:08 hours, a lone Japanese aircraft materialized through cloud cover. The Yokosuka D-4Y Judy dive bomber appeared at 2,500 feet altitude. Ship's radar had missed its approach among returning American aircraft clutter. Combat air patrol focused on threats from different vectors. No interceptors moved to engage the intruder. Anti-aircraft gun crews tracked multiple contacts elsewhere. They had no time to train weapons before the enemy pilot committed to his attack dive. His identity would never be established. Perhaps 30 seconds remained from pushover to impact. In that brief span, he released two 500-pound semi-armor-piercing bombs with devastating accuracy. Then, he vanished back into protective cloud cover before anyone could track his escape route. He had achieved every Japanese aviator's dream: a perfect attack run against an American carrier. Whether he survived to report success remains unknown. The first bomb struck flight deck centerline. 15 feet forward of the island superstructure, it punched through 3-inch wooden planking like paper. Steel deck beneath offered no resistance. Detonation occurred in the hangar deck below. Blast waves traveled at 26,000 feet per second. They tore through packed aircraft like a giant invisible fist. Aviation gasoline ignited instantly. Fireball engulfed everything within 50-foot radius. Explosions sent number 1 elevator rocketing skyward. The 4-ton steel platform measured 60 feet by 34 feet. It rose 400 feet into morning air. End over end, it tumbled like a massive coin flip. Then, gravity reclaimed it. The elevator crashed back onto deck surface. Impact shattered it into deadly fragments. Metal shards tore through aircraft and human flesh alike. Secondary explosions rippled across the hangar as fuel tanks ruptured in sequence. Ordnance began cooking off in the rising heat. The second bomb found its target among 31 aircraft warming for launch. Direct contact with flight deck triggered instant detonation. Holocaust erupted across the after section. 31 fuel tanks exploded in rapid succession. Each explosion fed the next in a chain reaction of destruction. Fireball rolled across deck surface like a breaking wave of liquid flame. Sailors on nearby ships felt their vessels rock from explosion force. Blast waves knocked men off their feet on destroyers 1,000 yards distant. On Franklin's flight deck, pilots trapped in cockpits faced instant death. Some managed to unbuckle harnesses and dive overboard into the sea. Others burned where they sat. Their screams disappeared in the roar of exploding fuel and ammunition. The next 30 seconds would determine Franklin's fate. In the hangar deck, where the first bomb detonated, fires spread with terrifying velocity. Gasoline from ruptured tanks flowed across steel decking. It sought any opening like liquid death. Ventilation ducts provided the perfect pathway. Within seconds, burning gasoline vapor was being pumped throughout the ship. Automatic ventilation systems continued operating. They spread destruction to every compartment. Heat ignited ready ammunition stored near aircraft positions. 20-millimeter rounds began cooking off in the flames. Red tracers streaked through smoke like deadly fireflies. 40-millimeter shells exploded with grenade force. Shrapnel hurled through the hangar space. Men trying to reach firefighting equipment fell cut down by their own ammunition. Then, tiny TIM rockets began igniting in the inferno. These massive experimental weapons weighed 1,300 pounds each. No one understood their behavior in fire conditions. Solid fuel motors were designed to burn at 5,000 degrees Fahrenheit. 6 seconds of burn time produced 50,000 pounds of thrust each. When the first rocket ignited at 7:11, the motor screamed to life. The sound cut through roar of fire and explosion. The 11-foot missile shot horizontally across deck like a meteor. Flame trailed behind its passage. It punched through half-inch steel plating of island structure like tinfoil. Explosion on starboard side showered deck with molten metal fragments. More rockets followed in random sequence. They screamed in every direction without guidance. Some plunged into ocean waters. Others smashed through bulkheads deeper in the ship. One rocket cut a gun crew in half before exploding in the water beyond. Another rocketed the full length of flight deck and disappeared over the bow. The deck became a killing ground where men died from fire explosion or random weapon trajectories. Lieutenant Commander Stephen Jurica Jr. was in his sea cabin below the bridge when bombs struck. The navigator had graduated Naval Academy in 1930. He served as intelligence officer on USS Hornet during Doolittle's raid. Experience taught him to recognize disaster instantly. The distinctive double thump of bomb detonations, followed by rolling thunder of secondary explosions, told the complete story. He grabbed life jacket and battle helmet, then ran for the bridge. What greeted him, topside, would haunt his remaining years. The after two-thirds of flight deck had become a sea of flame. Aircraft exploded in sequence. Some launched themselves into ocean as engines caught fire and ran at full throttle. Propellers screamed in final mechanical death throes. Wooden deck planking burned, adding fuel to the inferno. Holes gaped where bombs and rockets had penetrated deck surface. Some openings measured large enough for men to fall through. Personnel were on fire, running, rolling, jumping over the side. The list to starboard was already noticeable. Perhaps 5 degrees and increasing steadily. Black smoke boiled from hangar deck openings. Density obscured the after portion of ship structure. Every few seconds, another Tiny Tim rocket would ignite. Each one screamed across deck, on unpredictable trajectory. Death came from any direction without warning. Jurica began organizing damage control parties from stunned survivors. Forward section of flight deck remained relatively clear of flames. Creating a fire break might save the bow section. Resources were desperately limited. Jurica made one of warfare's hardest decisions. He ordered all personnel to abandon the after-flight deck. All efforts would concentrate on saving forward two-thirds of ship structure. The order meant leaving wounded men behind in flames. It meant letting fires burn that might have been fought, but it focused limited resources where they might make actual difference. 4 decks below, in engineering spaces, Lieutenant Junior Grade Donald Gary stood watch as engineering officer. The forward engine room hummed with mechanical precision when bombs struck above. Gary had graduated Naval Academy in 1943. He had served aboard Franklin less than 4 months. But those months included October 30th, 1944, when kamikaze attack killed 56 men. He understood what carrier damage looked like firsthand. He felt the ship shudder twice from bomb impacts. Shock waves transmitted through hull structure into his boots. Immediate roar of secondary explosions followed. Engineering watchstanders looked to him for direction. Their faces showed fear and uncertainty. Gary's first priority was keeping power plant operational. Franklin had been making 25 knots speed. 8 Babcock and Wilcox boilers delivered maximum steam. 4 turbines drove propeller shafts at full capacity. Now explosions on upper decks sent shock waves through ship structure. Fuel oil lines ruptured under stress. Steam lines fractured from impact damage. Most critically, ventilation systems began pumping smoke into engineering spaces. Conventionally designed ships offered 2 choices to engineering crews: abandon machinery spaces and lose all power, or stay at station and suffocate from smoke inhalation. Gary identified a third option through careful analysis. Extensive compartmentalization built into Essex-class design allowed forward engine room isolation. He ordered crew to seal all ventilation ducts immediately. Emergency breathing apparatus was distributed to all hands. Portable air bottles normally used for firefighting would sustain life. Men would work breathing from bottles while maintaining machinery. Gary made systematic evaluation of remaining functional systems. 2 boilers in forward boiler room remained operational. 3 of 4 turbines could still turn propeller shafts. Electrical systems were failing in sections as fires burned through cables. But generators in undamaged compartments continued running. Ring main electrical distribution allowed power rerouting around damaged sections. Gary made the decision that would ultimately save his ship. Instead of abandoning station, he would maintain engineering plant operation. As long as Franklin had power, she retained fighting chance. Power meant pumps for firefighting throughout the ship. Power meant ventilation for damage control parties. Power meant steering control from the bridge. Most importantly, power meant propulsion capability. Ships that moved under their own power had options dead ships did not possess. But his crew was suffocating despite emergency measures. Smoke infiltration overwhelmed their defenses. Portable air bottles would not last much longer. Gary recalled details from engineering training and ship construction specifications. The CO2 flooding system designed for fuel storage compartment fires could theoretically be modified. Jury rigging might provide positive pressure ventilation. This represented theoretical possibility never tested under actual conditions. The system was designed to pump carbon dioxide, which would kill them instantly. But isolating CO2 bottles and substituting high-pressure air bottles from damage control systems might work. He could flood engine room with breathable air under positive pressure. This would force smoke out through sealed ventilation ducts. With crew members collapsing from oxygen deprivation, Gary began manual valve and pipe rerouting. He converted fire suppression system into life support system through desperate improvisation. His hands shook from lack of oxygen as he worked. Finally, he opened the critical valve. High-pressure air flooded the sealed space. Pressure gauge climbed steadily upward. Sealed hatches held against internal pressure. Smoke began venting through small gaps around ventilation dampers. Within 2 minutes, air cleared enough for normal breathing. Forward engineering spaces sealed and pressurized became habitable island in ship filled with death and destruction. On hangar deck, Father O'Callaghan was blown off his feet by first explosion force. The 43-year-old Jesuit priest had taught physics and mathematics at Holy Cross College before the war. Worcester, Massachusetts seemed very distant now. He found himself lying in a pool of burning gasoline. His uniform was catching fire around the edges. He rolled across steel deck, smothering flames against metal surface, then struggled to his feet amid chaos and destruction. Around him, hangar deck had transformed into vision of hell. The space measured 654 feet long and 70 feet wide. Ceiling height was 17 feet 6 inches. Overhead, maze of pipes, cables, and ventilation ducts now dripped molten metal. The entire space filled with flame and choking smoke. Aircraft burned with aluminum skin melting and dripping like metallic wax. Ammunition exploded continuously in staccato roar. Tiny Tim rockets shrieked above the general din. Heat intensity was so extreme that 2.5-inch special treatment steel plates began glowing red in spots. O'Callaghan understood what he witnessed, despite impossible implications. The hangar deck was not collapsing under extreme conditions. STS plates were not warping or buckling, despite temperatures that should have melted mild steel. Fire, horrific as it appeared, remained largely confined to hangar level. It was not burning through to third deck below. Steel structure was not failing catastrophically. Ship framework was holding together. O'Callaghan, with white chaplain helmet marked by black cross, began moving through flames. He administered last rites to dying men around him. His voice rose above the mechanical roar. Through this holy anointing, may the Lord in His love and mercy help you with the grace of the Holy Spirit. May the Lord who frees you from sin save you and raise you up. Then he began organizing survivors into effective teams. Men stood around, stunned, waiting for orders from authority. O'Callaghan provided that authority with calm direction. Form bucket brigades for firefighting. Throw ammunition overboard before it cooks off completely. Move wounded men to forward elevator for evacuation. Run hoses from fire main systems throughout the ship. Hangar sprinkler system had been damaged by shrapnel. Pipes were torn and leaking uselessly, but portable pumps could still draw from 4 independent fire main systems. Men hauled heavy hoses toward advancing flames. Rubber hoses became so hot they burned through protective gloves. Others began throwing burning aircraft overboard through hangar deck openings. Tractors pushed flaming wreckage through 60-foot-wide doors into ocean. O'Callaghan moved through fire that melted rubber soles of his shoes. He directed efforts with calm authority of mathematics professor, explaining complex theorem. He became legend in those desperate minutes. Years later, survivors would remember him as figure from medieval stories. Warrior priest who seemed completely immune to fear and death. But O'Callaghan later told interviewers he was terrified every single moment. What kept him moving forward was simple realization about ship survival. Franklin was enduring punishment beyond all expectation. Despite fires that should have caused catastrophic structural failure, she remained afloat. Despite explosions that should have broken her back, she was still fighting. If ship could hold together, he could hold together. On bridge, Captain Garris organized command response to disaster. The 54-year-old officer had entered Navy as enlisted man during World War I. He worked his way up through ranks to naval aviator and ship command. He understood immediately how desperate their situation had become. All radio communications were dead cut by fire damage. Combat Information Center was completely destroyed. Radar systems were failing one by one as fires reached electronic components. Ship was taking pronounced list to starboard, now approaching 10 degrees. Fire was spreading despite desperate containment efforts. Most ominously, Damage Control Central reported fires burning in multiple compartments from hangar deck down to third deck level. Franklin was burning from inside out like giant torch. Garris made first of several controversial command decisions. He ordered all non-essential personnel topside immediately. Prepare to abandon ship if situation deteriorated further. Hundreds of men poured up from below decks. Some showed burn injuries. Others carried wounds from shrapnel and explosion. Many appeared simply terrified by circumstances. They gathered on forward flight deck and forecastle away from spreading flames. Some jumped overboard without specific orders. They chose ocean over fire as lesser evil. Others were blown overboard by continuing explosions throughout ship structure. Within 20 minutes of initial attack, over 800 men were in water. Some swam away from burning hulk. Others clung to debris and life rafts awaiting rescue. USS Pittsburgh cruiser under Captain John E. Gingrich steamed 500 yards off Franklin's port beam. Gingrich maneuvered his ship to shield Franklin from Japanese coastline. He prepared for emergency towing operations if required. By 0730, just 22 minutes after attack, Pittsburgh had passed steel towing cable to Franklin. She began taking carrier in tow, pulling away from Japanese coast, at 5-knot speed. Progress was agonizingly slow, but it represented movement away from danger. Every mile increased survival chances significantly. USS Santa Fe cruiser under Captain Harold C. Fitz made incredibly brave rescue maneuver. He brought his 10,000-ton cruiser alongside burning carrier. Starboard side to starboard side, positioning for personnel transfer. Fire and explosions continued every few seconds on Franklin. Carrier was listing toward his ship, creating collision danger. Fitz held Santa Fe in position for over 1 hour. As two ships ground together, rolling in ocean swells, men jumped across gap between vessels. Carrier crew leaped from higher deck to cruiser below. Others were lowered on stretchers by rescue parties. Santa Fe crew formed teams that actually boarded Franklin. They helped carry wounded personnel to transfer point at rail. By time Santa Fe pulled clear at 900 hours, she had rescued 832 men from Franklin. This included 103 wounded requiring immediate medical attention. Her white-painted hull was scorched black from intense heat exposure. Superstructure showed dents where she ground against carrier hull. But she had saved 832 lives from certain death. At 800 hours, 2 hours after initial attack, Franklin's situation appeared hopeless to all observers. She was dead in water, except for Pittsburgh's emergency tow. List had increased to 13 degrees starboard, creating stability concerns. Fire and smoke engulfed her from island structure, aft to stern. Explosions continued as ammunition cooked off in spreading fires. Forward elevator, blown from its shaft, lay twisted across flight deck. After elevator had been blown completely off ship into ocean. Holes gaped in flight deck, some measuring 20 feet across. Radio Tokyo, monitoring American communications, announced large American carrier had been sunk off Japan. Japanese submarines in area received orders to locate and finish off the wreck. Every man still aboard Franklin understood they were witnessing death agony. Every observer on surrounding ships knew carriers did not survive this kind of damage. History provided no examples of such survival against such odds. Everyone understood the situation completely. But down in the forward engine room, Donald Gary was accomplishing something that defied all expectations. His engineering crew worked alongside him in their sealed compartment. They breathed pressurized air that tasted of metal and oil. The air was thick and heavy in their lungs. Gary had managed to bring steam pressure back to 2 of the forward boilers. The boilers hissed and rumbled with renewed life. Steam coursed through pipes that had seemed permanently dead. The sound of pressurized steam filled the compartment with hope. 3 turbines were now spinning. Their massive rotors turned with increasing speed. The vibration traveled through the deck plates under the crew's feet. Power flowed through the ship like blood returning to a dying patient. The electrical system had been patched together through emergency damage control cables. These thick black cables snaked through passageways and compartments. They carried precious electricity to critical systems throughout the forward sections of the ship. Every wire had been hand-spliced by skilled electricians working in near darkness. At 0800 hours, Gary made contact with the bridge. He used the sound-powered phone system. This was the only communication method still functioning throughout the ship. The phone system required no electrical power. It operated purely through mechanical vibrations transmitted along steel cables. His voice crackled through the handset to the bridge. Bridge from forward engine room. I have steam on 2 boilers. 3 turbines are operational. Can make turns for revolutions equivalent to 2 knots. 2 knots represented almost nothing in terms of speed. A person could walk faster than 2 knots, but it meant propulsion. It meant the ship could move under her own power instead of being towed helplessly through the water. Captain Gary received this report and faced his most critical decision of the day. The weight of command pressed down on his shoulders. Every man's life depended on what he decided next. He gave the order that shocked everyone within hearing distance. Pittsburgh, cast off the tow. Franklin will proceed under her own power. The decision seemed to border on insanity. A carrier that was dead in the water just hours before couldn't possibly make way on her own. Fire still raged in multiple compartments. Explosions continued to rock the ship at irregular intervals. Smoke poured from dozens of holes in her deck. But Gary understood something fundamental about naval warfare. A ship that could move possessed a fighting chance. A ship under tow remained helpless. She moved only where the towing vessel took her. She had no control over her destiny. A ship under her own power could maneuver in response to threats. She could create airflow across her deck to blow smoke and heat away from critical areas. She could restore stability through speed and intelligent rudder control. Movement meant survival. At 0812 hours, Franklin's massive bronze propellers began their first tentative rotation. The engineering crew had succeeded in restoring power to the starboard shafts. These enormous propellers, each weighing several tons, bit into the Pacific water. The ship moved forward at barely 2 knots. She inched away from the Japanese coast like a wounded animal seeking safety. It represented one of the most remarkable moments in the entire history of naval warfare. A carrier that should have slipped beneath the waves was moving under her own power. The restoration of propulsion transformed everything about Franklin's situation. Movement, even painfully slow movement, created wind across the deck. The 25-knot winds generated by the ship's forward motion helped blow smoke and heat overboard. Instead of settling down into the ship's interior, the toxic smoke was carried away by the artificial wind. The improved airflow allowed damage control parties to operate more effectively in spaces that had been choked with smoke. The list began to improve as the engineering crew took control of counter-flooding. They deliberately flooded port-side compartments with seawater. This balanced the thousands of tons of water that had accumulated on the starboard side from intensive firefighting efforts. The ship slowly returned to a more stable attitude. Most importantly, the fact that Franklin could move gave her crew renewed hope. Men who had been preparing to abandon ship returned to their battle stations. If Franklin could move, she could be saved. If she could be saved, their shipmates had not died in vain. On the flight deck, Commander Jerrica led his damage control parties in a desperate innovation. They erected a water curtain across the deck at frame 110. This position was approximately 400 feet from the bow. Using every available fire hose they could locate, they created a barrier of spray between the forward section and the fires raging aft. The water curtain represented an innovation built into the Essex-class design. Navy architects had anticipated exactly this kind of emergency. The wall of spray absorbed the intense radiant heat that poured forward from the fires. It knocked down smoke that would otherwise have made the forward deck uninhabitable. The water barrier created a defensive line that firefighters could actually hold. Behind that protective curtain, the forward flight deck remained relatively intact and operational. But Franklin was far from being out of danger. At 0845 hours, one of the most devastating secondary explosions erupted deep within the ship. A magazine filled with 5-inch ammunition detonated below the hangar deck. The blast was absolutely catastrophic in its violence. Men aboard the screening destroyers thought Franklin had finally blown apart completely. A fireball rose 500 feet above the ship's superstructure. It formed a tower of flame and smoke, visible for 20 miles in every direction. The explosion killed dozens of men who had been fighting fires in that section. The blast blew a hole through 3 separate decks. It penetrated from the hangar deck down to the 3rd deck below. Metal fragments tore through spaces that had been undamaged until that moment. New fires started in compartments that had been secure. More men were wounded by flying debris. But something remarkable happened in the aftermath of this explosion. The bulkheads surrounding the magazine had all been constructed of special treatment steel. These barriers contained most of the blast force within the immediate area of the explosion. In a conventionally built ship, this explosion would have torn through mild steel bulkheads like paper. The destruction would have spread laterally throughout the ship. The blast probably would have broken the ship's back. Fragments would have penetrated adjacent spaces and detonated other magazines in a cascading catastrophe. But the STS bulkheads had been specifically designed to resist fragmentation. They channeled the explosion upward and outward instead of allowing it to spread sideways. The adjacent magazines remained completely intact. Their contents never ignited. The fire mains running through that section were severed by the blast, but the redundant mains in other sections continued to supply water pressure to firefighting teams. The ship shuddered violently from the explosion. Her entire structure groaned under the shock. But her fundamental framework held together. By 12:52 hours, which was 252 minutes after the initial attack, Franklin had begun to achieve some measure of stability. The fires were contained even if they weren't completely controlled. The list had been reduced to 9 degrees through careful counter-flooding operations. The engineering plant was delivering enough power for 4 knots of speed. Then, the speed increased to 6 knots as more systems came online. Then 8 knots as additional boilers were brought back into service. By noon, Franklin was making 15 knots through the water. The transformation was absolutely stunning to witness. A carrier that observers had watched dying throughout the morning was now moving at respectable speed. Her fires were mostly controlled. Her crew was beginning to organize recovery operations instead of abandonment procedures. By 1600 hours, 8 full hours after the attack began, the major fires were finally extinguished. Smoke still poured from the wreckage of the hangar deck. Small fires continued to flare as damage control parties discovered new pockets of burning material deep within the ship. But the Holocaust was over. Franklin had survived. The cost in human lives was staggering beyond comprehension. According to the most recent research conducted by naval historians, 724 men had been killed. Most died in the first 10 minutes of the attack when the hangar deck became an inferno. Another 265 men were wounded. Many suffered burns that would require months of intensive medical treatment. More than 30% of her entire crew was either dead or wounded. But Franklin was afloat. She was moving under her own power, and she was heading toward safety. Captain Garris pointed the bow southeast toward Ulithi Atoll. The base lay 2,500 miles away across the Pacific Ocean. Franklin began the long journey home, escorted by Pittsburgh and her screening destroyers. Her top speed was initially limited to 15 knots, but as the engineering crew made additional repairs and brought more boilers online, she would eventually achieve 25 knots. The ship could make it home. She would make it home. The voyage to Ulithi tested every aspect of the design philosophy that Homer Lenhart Ferguson had championed 5 years earlier. Franklin was essentially a floating wreck. She was barely seaworthy. She maintained a persistent list despite counter-flooding efforts. Massive holes gaped in her deck and hull, but she remained afloat because her fundamental structure had held together. The hangar deck had been subjected to fires that reached 2,000 degrees Fahrenheit. The steel showed severe warping from the intense heat. But there was no catastrophic buckling that would have caused structural failure. The beams supporting the deck had deformed visibly from the heat. Their shapes were permanently altered, but they had not failed completely. They continued to carry their structural loads. The flight deck was holed in 53 separate places. Some holes were small, others were large enough to drive a truck through, but the deck still supported the weight of damage control equipment. It held up under the hundreds of men working to make temporary repairs. The hull plating had been stressed by the list, the explosions, and the counter-flooding operations, but it maintained watertight integrity in all critical areas. Most remarkably, the underwater protection system had remained intact. This system had been designed to resist torpedo hits, but it had been subjected to enormous shock loads from internal explosions. Not a single critical bulkhead in the underwater protection system had failed. The ship's structural integrity remained sound. Franklin reached Ulithi on March 24th. This was 6 days after the attack that should have sunk her. She anchored in the peaceful lagoon. She was essentially a floating morgue, carrying 724 bodies. But she had arrived under her own power. Temporary repairs were conducted over 4 days. Work crews focused primarily on patching the flight deck holes and making the after sections of the ship weathertight. These repairs would allow her to survive the transit to Pearl Harbor. On March 28th, Franklin departed Ulithi bound for Pearl Harbor. She was still capable of 20 knots despite her extensive damage. The engineering plant functioned well enough to maintain this speed throughout the journey. She arrived at Pearl Harbor on April 3rd. Her arrival caused an immediate sensation throughout the naval base. Word of her survival had spread through Navy communications channels. But seeing the battered carrier enter the harbor under her own power was still absolutely stunning. The Navy conducted temporary repairs sufficient for the long transit through the Panama Canal. The journey would take her across the entire breadth of the American continent and into the Atlantic Ocean. On April 10th, Franklin departed Pearl Harbor under her own power. She was bound for the Brooklyn Navy Yard in New York. The transcontinental journey would test her seaworthiness one final time. She arrived at Brooklyn on April 28, 1945. This was nearly 6 weeks after the attack that had tried to kill her. At Brooklyn, the full extent of her damage could finally be assessed by Navy engineers and Bureau of Ships experts. War Damage Report Number 56 was compiled over the following months. This document meticulously catalogued the devastation Franklin had survived. The hangar deck had been completely destroyed across 40% of its total area. The flight deck was holed in 53 places. These holes ranged from 3 feet to 20 feet in diameter. Over 30% of the crew berthing spaces had been burned out completely. The steel bulkheads were warped by extreme heat. Everything inside these spaces had been reduced to ash and twisted metal. Thousands of structural members required replacement. The ventilation system needed to be completely rebuilt from scratch. The electrical system required extensive reconstruction throughout multiple decks. The damage was so severe that repairs would take 2 years at minimum. The cost would nearly equal building a completely new carrier, but the basic structure remained sound. Naval constructors examining the steel found the ship's frame straight to within acceptable tolerances. The hull plating maintained its integrity, despite the fires and explosions. The engineering spaces, though damaged by smoke and structural deformation from heat, were completely repairable. The frames and structural members showed stress from the ordeal, but there had been no catastrophic failure anywhere in the primary structure. Franklin could be rebuilt if the Navy chose to invest the resources. She would never be rebuilt because the war ended before repairs could begin. But she could have been restored to full operational status. That fact alone was remarkable. The Navy made a different decision about Franklin's immediate future. She represented the most heavily damaged aircraft carrier to survive the entire war. She was essentially a floating laboratory of battle damage. Rather than beginning immediate repairs, the Navy decided to use her as a test bed. Engineers needed to understand how carriers survived catastrophic damage. For months, technical experts crawled through her wreckage. They measured everything. They photographed every detail. They conducted extensive testing on damaged materials. They documented how special treatment steel behaved under extreme heat. They measured the deformation of structural members. They calculated the temperature gradients that had existed during the fire. They mapped exactly how the blast effects from the magazine explosion had been contained by STS bulkheads. They studied how the multiple independent fire mains had maintained water pressure even when large sections of the ship were destroyed. Every piece of data was collected, analyzed, and incorporated into massive reports. These reports would inform every carrier designed after the war. Franklin's agony became the foundation for improved survivability in future ships. But Franklin's survival wasn't the only validation of the Essex-class design philosophy. The class would prove itself in battle repeatedly during the final months of the war. Each engagement provided additional evidence of the design's superiority. USS Bunker Hill was hit by two kamikaze aircraft on May 11, 1945, off Okinawa. The damage killed 396 men and wounded 264 more. The attacks occurred within 30 seconds of each other. The first kamikaze crashed into planes being refueled on the flight deck. This caused massive fires similar to Franklin's experience. The second kamikaze penetrated to the gallery deck, spreading fire to interior spaces that had been undamaged. Bunker Hill's damage control teams fought fires for 5 continuous hours before bringing them under control. She, too, survived the ordeal. She made it back to port under her own power. Like Franklin, she was so heavily damaged that she never saw post-war service. But she did not sink. USS Intrepid survived 4 separate kamikaze hits during the war. She was hit on October 29, 1944, and repaired. Hit again on November 25, 1944, and repaired again. Hit a third time on March 18, 1945. Hit a fourth time on April 16, 1945. Each time her crew fought fires, made repairs, and returned to combat operations. She survived the war and served until 1974. She was finally decommissioned after 31 years of faithful service. She now serves as a museum ship in New York City. USS Enterprise, designated the Big E, became the most bombed, torpedoed, and otherwise damaged aircraft carrier in World War II that survived. She was hit by bombs at Eastern Solomons and Santa Cruz. She suffered damage in numerous other actions. She was nearly sunk by kamikaze attacks in May 1945. Each time her Essex-class structure and damage control systems saved her from destruction. She survived the war and served until 1947, when she was finally decommissioned. USS Hancock, USS Belleau Wood, USS Lexington, USS Wasp, USS Ticonderoga, and USS Randolph all took serious battle damage and survived. The common thread connecting all these survivals was the Essex-class design philosophy. The extensive use of special treatment steel throughout the structure made the difference. The comprehensive compartmentalization prevented cascading damage. The redundant firefighting systems kept water flowing to critical areas. The careful design made every structural element contribute to survival. None of these carriers sank during the war. None was abandoned as a total loss. All made it home to fight another day. This wasn't luck or coincidence. This was superior engineering applied to warship design. The contrast with carriers built to different standards was stark and well documented. The British armored carriers had been predicted by many pre-war experts to be more survivable than American designs. In practice, they proved less resilient. Their armored flight decks were made of 3-inch thick armor plate. This prevented bombs from penetrating to the hangar below. But when fires did start in the hangar from other causes, they became extraordinarily difficult to fight. The armored deck above and armored hangar sides below created an oven effect. Heat and smoke were contained rather than vented. The ventilation systems couldn't handle these extreme conditions. Firefighting parties couldn't operate effectively in the superheated environment. Damage that an Essex-class carrier could repair in days kept British carriers out of action for weeks. HMS Formidable was hit by kamikazes twice in 1945. The armored flight deck prevented penetration both times, but fires in the hangar caused by burning gasoline from the crashing aircraft forced the ship to withdraw from operations. HMS Illustrious was knocked out of action repeatedly by damage that would have been considered moderate by Essex-class standards. HMS Victorious and HMS Indomitable suffered similar problems throughout their service. The British carriers were undoubtedly tough, but their armor philosophy made them less adaptable and more vulnerable to mission kill. They might survive the initial impact, but couldn't continue fighting. The Japanese carrier force had begun the war with some of the finest carriers in the world, but they suffered from design limitations imposed by treaty restrictions and lack of combat experience in damage control. At Midway in June 1942, 4 Japanese fleet carriers were sunk by bomb hits that an Essex-class carrier would likely have survived. Akagi, Kaga, Soryu, and Hiryu all went down after being hit by 1,000-pound bombs that penetrated to their hangar decks. The Japanese carriers lacked adequate compartmentalization. Their firefighting systems were primitive compared to American designs. They had minimal structural protection against internal explosions. They were essentially floating bombs waiting to detonate. Once cascading explosions started in a Japanese carrier, there was no effective way to stop them. The ships were designed for speed and striking power, not survival. By 1945, Japan had no fleet carriers left capable of offensive operations. America had 20 Essex-class carriers operational in the Pacific. The statistical record of the Essex-class speaks to Ferguson's vision with brutal clarity. 24 ships of the class were completed during the war. 14 saw combat in World War II. They were hit by bombs, torpedoes, and kamikaze aircraft a total of 39 times. They suffered damage that killed over 2,600 men total across the entire class. Not one sank. Not one was abandoned as a constructive total loss. Every damaged Essex-class carrier was repaired and returned to service, except Franklin and Bunker Hill. These 2 were kept in reserve after the war ended, because repairs weren't urgently needed for peacetime operations. The class earned a total of 143 battle stars for combat service. They served in every major Pacific campaign from Tarawa to Tokyo Bay. They formed the backbone of American naval aviation throughout the Pacific War. But who was the man behind this remarkable design? Homer Lenhart Ferguson was born in Waynesville, North Carolina, on March 6, 1873. His family had deep roots in the mountains of western North Carolina. At the unusually young age of 15, he entered the United States Naval Academy at Annapolis. Even for that era, when midshipmen entered younger than today, 15 was exceptionally young for appointment to the academy. He graduated in 1892. Some sources report he graduated at the head of his class. Other sources suggest he graduated third in his class. The historical records are ambiguous on this point. What is absolutely clear is that he graduated with high honors. He was immediately selected for advanced study rather than being sent to sea duty. The Navy recognized his exceptional intellectual ability. Instead of joining a ship's company, he was sent to Glasgow University in Scotland. Ferguson studied at Glasgow from 1892 to 1895. He pursued naval architecture and marine engineering under the renowned Scottish ship designers. These men were the acknowledged leaders in their field throughout the world. Glasgow in the 1890s was the absolute center of the world shipbuilding industry. Scottish yards built the fastest ships afloat. They built the most advanced ships afloat. They built ships that established speed records and endurance records. Ferguson studied under professors who had designed blockade runners for the Confederacy during the American Civil War. These had been fast ships that used innovative iron frames and revolutionary hull designs. They had to be fast to evade Union warships. They had to be tough to survive rough weather. He learned stress analysis, hydrodynamics, metallurgy, and advanced structural design. He absorbed the Scottish philosophy that ships should be built to survive above all other considerations. A ship might be fast or heavily armed, but if she sank, she could not complete her mission. Build ships that survive, his professors told him repeatedly. This lesson would stay with Ferguson for his entire career. Ferguson returned to the United States in 1895 with the finest maritime engineering education available anywhere in the world. He began his career as a naval constructor, applying his theoretical knowledge to practical shipbuilding problems. He worked at the Columbian Iron Works in Baltimore, learning how commercial shipbuilding differed from naval construction. He worked at Navy yards in Portland, Oregon, Bremerton, Washington, and Bath, Maine. He supervised construction of battleships and cruisers. He learned the practical realities of how ships were actually built versus how they appeared on engineering drawings. Theory was one thing. Practice was entirely different. Materials didn't always behave as calculations predicted. Workers didn't always execute designs with perfect precision. In 1902, Ferguson joined Newport News Shipbuilding. This was then a relatively small yard in Virginia. It had been founded by railroad magnate Collis P. Huntington in 1886. Ferguson started as assistant superintendent of construction. His engineering skill became apparent immediately. His leadership ability was equally obvious. He understood both the technical aspects of shipbuilding and the human aspects of managing large workforces. In 1905, at age 32, Ferguson resigned from the Navy to become a full-time civilian employee at Newport News. He rose rapidly through the company hierarchy. By 1914, he was vice president under President Albert Lloyd Hopkins. On May 7, 1915, Hopkins was traveling to England on shipyard business. He was aboard RMS Lusitania when the liner was torpedoed by a German submarine off the Irish coast. Hopkins died when the ship sank. He was one of 1,198 victims of the attack. Ferguson had been expected to someday succeed Hopkins, but Hopkins's sudden death thrust Ferguson into leadership much earlier than anyone had anticipated. On July 22, 1915, at age 42, Homer Ferguson became president of Newport News Shipbuilding. He would hold that position for the next 31 years. He would lead the company through World War I, the Great Depression, and World War II. His tenure would transform Newport News into America's premier naval shipyard. Under Ferguson's direction, the yard built 7 of the 16 battleships in Theodore Roosevelt's Great White Fleet. This fleet circumnavigated the globe from 1907 to 1909, demonstrating American naval power to the world. During World War I, Ferguson oversaw emergency shipbuilding programs that delivered 25 destroyers to the Navy. These ships were built in record time using innovative construction techniques that Ferguson personally developed. He also pioneered worker welfare programs that were revolutionary for their time. In 1918, concerned about housing for shipyard workers, Ferguson worked with the federal government to create Hilton Village. This was one of America's first planned communities. He formalized the Newport News Apprentice School in 1919. This created a training program that became a national model for technical education. The Apprentice School still operates today, training the next generation of skilled shipbuilders. But Ferguson's most important contribution came in the late 1930s. War clouds were gathering over Europe and Asia. The Navy began planning a new generation of aircraft carriers to replace the treaty-limited designs of the 1920s. The Essex class, as it would eventually be called, would become the backbone of America's carrier fleet. Ferguson saw an opportunity to revolutionize warship design completely. He had developed a radical idea over his decades of experience. Use armor as structure. Traditional naval architecture treated armor as dead weight. Protective plating was added on top of the structural hull. Armor protected the ship, but contributed nothing to structural strength. Ferguson argued the exact opposite approach. If you used special treatment steel throughout the ship, you could create a vessel where every plate contributed to both strength and protection simultaneously. Every structural member would also be armor. Every piece of armor would also carry structural loads. Special treatment steel had been developed by Carnegie Steel around 1910. It was a nickel-chromium steel alloy with remarkable properties. It possessed the protective qualities of Class B armor plate. It could resist fragmentation and provide significant protection against shell splinters and bomb fragments. But unlike traditional armor plate, STS was ductile enough to be fabricated as structural steel. It could be bent into complex shapes. It could be welded using standard techniques. It could be formed into structural members that carried loads throughout the ship. Most importantly, it could be used throughout a ship wherever strength was needed. The problem was cost. STS was vastly more expensive than mild structural steel used in conventional construction. The cost jumped dramatically when Ferguson proposed using special treatment steel throughout the entire vessel, perhaps 30% more expensive than conventional construction methods. The exact price depended on thickness requirements and technical specifications. Installing STS in every structural component of a carrier would push expenses far beyond what Navy budget planners wanted to authorize. The Bureau of Ships took one look at Ferguson's initial proposals and rejected them immediately. Too expensive, they declared. The cost was simply prohibitive for widespread implementation across the fleet. Ferguson refused to accept this rejection. He returned with detailed engineering calculations that challenged every assumption about cost versus benefit. His numbers told a different story than the Bureau had expected. An Essex-class carrier built entirely with special treatment steel would actually weigh less than conventional designs. This seemed impossible at first glance. How could stronger, thicker steel reduce overall weight? The answer lay in structural engineering principles. Armor-grade steel contributed directly to the ship's structural strength. Every bulkhead, every frame, every deck beam served dual purposes. They provided structural support while simultaneously offering protection against battle damage. This dual function meant designers could eliminate redundant structural members. The armor itself became the structure. The structure itself became the armor. Weight savings emerged from this integration of functions. Lower weight meant better performance characteristics. The ship could carry more aircraft without exceeding displacement limits. More fuel could be stored without affecting stability. Ammunition capacity increased without compromising speed or maneuverability. Most importantly, Ferguson argued, structural redundancy created by using armor-grade steel everywhere meant battle damage that would cripple conventional carriers might prove survivable. You wouldn't save money during construction, Ferguson admitted frankly to Navy planners. The initial expense would be substantial, but you would save lives in actual combat operations. You might even save the entire ship when enemy action would otherwise sink it. These benefits justified the additional construction costs. Ferguson found powerful allies among naval officers who had studied the early carrier losses of the Pacific War. These men understood that survivability mattered more than any other single design factor. Ships that sank couldn't complete their missions. Dead crews couldn't fight battles. Lexington had been lost at the Battle of the Coral Sea in May 1942. The initial Japanese torpedo hits hadn't destroyed her immediately. She had continued operating for hours after the attack. Her crew had fought fires and controlled flooding with remarkable skill and determination. But vapor explosions from damaged aviation fuel systems finally doomed the great carrier. Hours after the initial attack, secondary explosions tore through her hull. The crew abandoned ship as flames consumed everything combustible. Lexington slipped beneath the Pacific waves with most of her aircraft still aboard. Yorktown had also been damaged at Coral Sea, taking significant bomb and torpedo damage during the battle. But her crew had brought her safely back to Pearl Harbor, where shipyard workers performed miraculous repairs in just 48 hours. Welders worked around the clock. Damage control teams sealed compartments and rerouted systems. Yorktown steamed out of Pearl Harbor to fight again at Midway, barely 3 days after limping into port with serious structural damage. At Midway, she survived multiple bomb hits and torpedo strikes. Her crew nearly saved her through heroic damage control efforts, but a Japanese submarine found her while under tow, still fighting for survival. A final torpedo finished what the aircraft had begun. Yorktown rolled over and sank, taking with her the dreams of her crew who had fought so hard to save their ship. Both carriers might have survived with better damage control systems and more robust structural designs. Their losses demonstrated the critical importance of survivability in carrier operations. The Navy approved Ferguson's modified design based on these harsh lessons from combat. The hangar deck would be constructed from 2.5 inches of special treatment steel instead of Ferguson's originally proposed 1.5 inches. This increase reflected combat experience showing that hangar fires posed the greatest threat to carrier survival. The fourth deck, forming the bottom boundary of the hangar box, would use 1.5 inches of STS throughout its entire area. This deck had to contain fires and explosions from above while maintaining structural integrity under extreme stress. The flight deck would rest on a framework constructed entirely of special treatment steel beams. Every support member, every connection point, every structural element would be built to withstand battle damage while continuing to function. The armor belt protecting the waterline would employ 4-inch Class B armor plate, backed by additional layers of STS. This combination would defeat most torpedo warheads while providing redundant protection against underwater explosions. Interior bulkheads throughout the entire ship would be constructed of special treatment steel wherever structurally possible. Every compartment boundary, every passageway wall, every internal barrier would contribute to overall survivability. The underwater protection system presented special challenges. This complex arrangement of compartments was designed to absorb torpedo hits through controlled flooding and energy dissipation. The critical holding bulkhead formed the final barrier against the sea. This bulkhead had to hold even when everything outboard had been destroyed. Ferguson specified thick special treatment steel for these vital barriers. If the holding bulkhead failed, the ship would flood beyond any hope of survival. No expense could be spared on this critical component. In total, each Essex-class carrier would incorporate thousands of tons of special treatment steel throughout its structure. The exact figures varied from ship to ship depending on specific configurations and modifications. Engineering estimates suggested between 3,000 and 4,000 tons per vessel. Unclassified documents don't specify precise tonnages, but the scale of special steel usage was unprecedented in naval construction. Every major structural component incorporated armor-grade materials where technically feasible. The financial cost was enormous by Depression-era standards, but the result was a ship where every structural member contributed directly to combat survival. No component served only one purpose. Everything worked together to keep the ship fighting. Ferguson pushed additional innovations beyond just special treatment steel applications. The Essex class would feature the most extensive compartmentalization of any aircraft carrier built to that time period. Traditional carrier design philosophy emphasized large open spaces for operational efficiency. Flight operations required vast hangar areas. Aircraft maintenance needed unobstructed workspaces. Administrative functions benefited from open offices and meeting areas. Ferguson insisted on the opposite design philosophy. Divide every possible space. Make every passageway a potential fire break. Create barriers wherever structural requirements permitted. Turn the ship into a honeycomb of separate, controllable compartments. Essex-class carriers were built with extensive compartmentalization throughout their entire internal volume. Hundreds of separate compartments could each be isolated, flooded, or ventilated independently of adjacent spaces. Available sources don't specify exact compartment counts, but the design philosophy was crystal clear. You should be able to lose multiple adjacent compartments and still maintain overall buoyancy and stability. Damage to one area couldn't be allowed to spread throughout the ship. The firefighting system represented a revolutionary approach to damage control. Traditional carriers relied on a single fire main running the full length of the ship. This main supplied water to firefighting stations throughout the vessel. If enemy action cut this main, entire sections would lose firefighting capability immediately. Crews would face raging fires with no water supply to combat them. Many early war losses resulted from exactly this scenario. Ferguson designed a system utilizing multiple independent fire mains. Each main was fed by multiple pumps located in different engine rooms. Each could be cross-connected or isolated through a complex network of valves and control systems. The system incorporated 9 separate fire pumps throughout the ship. Each pump could deliver thousands of gallons per minute to any section requiring water for firefighting operations. If one pump failed, others could compensate automatically. If enemy action severed one section of fire main, water flow could be rerouted through alternative paths. Multiple backup systems ensured that some firefighting capability would remain available even under the worst damage scenarios. The hangar deck received an overhead sprinkler system capable of deluging the entire space with seawater. This system could activate automatically when fires were detected, or manually when damage control teams needed immediate flooding capability. Water curtains could be erected instantly to create barriers against fire and smoke advancement. These curtains formed walls of falling water that fires couldn't penetrate. Smoke and toxic gases were trapped behind these liquid barriers. The carbon dioxide flooding system could pump inert gas into fuel storage compartments to suppress fires through oxygen displacement. This system prevented fuel fires from starting even when compartments were damaged and fuel was spilled. Emergency ventilation systems served dual functions. They could pressurize spaces to keep smoke and toxic gases out of critical areas like the bridge and engine rooms. Alternatively, they could ventilate spaces to remove smoke and gases after fires were extinguished. Every aspect of the damage control system was designed with redundancy as the primary consideration. Multiple backups existed for every critical function. The design assumed that damage would occur and primary systems would fail, but the ship had to survive anyway. The first Essex-class carrier, USS Essex CV-9, was laid down on April 28, 1941, at Newport News Shipbuilding. Ferguson's shipyard served as the lead builder for the entire class, responsible for establishing construction standards and procedures. The ship was completed in just 20 months of intensive construction effort. She was commissioned on December 31, 1942, ready for combat operations in the Pacific Theater. Her rapid construction demonstrated the efficiency of Ferguson's design and building methods. USS Yorktown CV-10 carried the name of one of the carriers lost at Midway. She was laid down at Newport News on December 1, 1941. Her keel was positioned just 6 days before the Pearl Harbor attack changed everything. Yorktown was commissioned on April 15, 1943, with Captain Joseph J. Clark commanding. Her crew knew they sailed in a ship named for heroes who had died fighting. This knowledge gave special meaning to their training and preparation. USS Franklin CV-13 was laid down at Newport News on December 7, 1942, exactly 1 year after Pearl Harbor. The date was chosen deliberately to commemorate the attack that had brought America into the war. Franklin was launched on October 14, 1943. Lieutenant Commander Mildred H. McAfee, director of the Waves Women's Naval Reserve, served as the ship's sponsor during launching ceremonies. This was unusual recognition for the women serving their country in naval roles. Franklin was commissioned on January 31, 1944, ready to join the growing fleet of Essex-class carriers heading toward Japan. Her crew trained intensively for the combat operations that lay ahead. None of Ferguson's innovations had been proven in actual combat when the first Essex-class carriers steamed into Pacific waters during 1943. Everything remained theoretical. Calculations existed on paper. Design choices had been made in drawing offices and shipyards thousands of miles from any battle. The ships looked impressive, tied up at docks or during sea trials. Their armor gleamed under fresh paint. Their compartments seemed strong and well-designed. Their damage control systems tested perfectly during exercises. But would they really survive when tested by enemy action? Would the special treatment steel actually stop bombs and torpedoes? Would the compartmentalization contain real fires and flooding? Would the redundant systems continue functioning when battle damage destroyed primary equipment? The answer came through battle after battle throughout 1943, 1944, and 1945. The Essex-class carriers faced every test that combat could impose. Japanese bombs fell on their decks. Torpedoes struck their hulls. Kamikaze aircraft crashed into their superstructures. They survived. When hit by suicide attacks that would have sunk earlier generation carriers, they remained afloat and operational. When fires raged through their hangars, consuming aircraft and fuel and ammunition, the damage control systems worked exactly as Ferguson had designed them. When bombs penetrated their armored decks and exploded in their interior spaces, the compartmentalization contained the damage within manageable areas. Flooding was controlled. Fires were extinguished. Operations continued. The Essex class became the most successful aircraft carrier design in naval history. 24 ships were built. They served through World War II, Korea, Vietnam, and beyond. Their success came precisely because Homer Ferguson had insisted on building ships that could survive anything. Ferguson remained president of Newport News Shipbuilding until July 31, 1946. He retired at age 73, having witnessed his carriers survive every test that combat could impose. His design philosophy had been validated through the most demanding trials possible. After retirement, Ferguson remained active in the Newport News community, where he had spent his entire career. He was instrumental in founding the Mariners Museum in Newport News, working alongside Anna Hyatt Huntington and her husband Archer M. Huntington. Ferguson served on the museum's board of directors and helped build its collections. The museum documented the complete history of shipbuilding and maritime commerce. Ferguson wanted future generations to understand the technical challenges that shipbuilders had overcome. He died on March 14, 1953, just 1 week after celebrating his 80th birthday. His passing marked the end of an era in American naval architecture and shipbuilding excellence. Ferguson received no Medal of Honor for his contributions to victory. No Navy Cross was awarded for saving thousands of lives through superior engineering. No congressional recognition acknowledged his role in the war effort. His name appears on no warships or naval facilities. The general public never learned who he was or what he had accomplished. His contributions were too technical, too abstract, too far removed from the visible drama of battle to capture popular imagination or media attention. But the men who survived Franklin's ordeal never forgot what Ferguson had done for them. They understood that their survival had been determined years before the battle. In drawing offices and fabrication shops, where decisions were made about steel thickness and compartment design. In the decades following the war, Franklin's survivors organized regular reunions to maintain the bonds forged through shared trauma and miraculous survival. The first reunion was held in 1947 in New York City. About 200 men attended that initial gathering. They shared stories that had been too painful to tell their families. They remembered shipmates who hadn't survived. They marveled at their own continued existence when so many others had perished. The reunions continued annually for many years as the survivors built new lives in civilian occupations. As they aged and their numbers decreased, the gatherings became less frequent. Every few years, then every 5 years, then longer intervals between meetings. The gatherings grew smaller as natural attrition claimed members of their exclusive brotherhood. But the bonds formed through shared survival remained stronger than time or distance could weaken. They had experienced something together that no one else could fully understand. In 1995, on the 50th anniversary of the attack, approximately 80 survivors gathered in Charleston, South Carolina. Half a century had passed since the fires and explosions that had nearly claimed their lives. They visited the USS Yorktown Museum ship, an Essex-class carrier like Franklin. Walking the decks of a sister ship, seeing the compartments and fire mains and structural details, they understood more deeply than ever before how they had survived. The engineering was visible in ways it had never been when they served aboard Franklin during wartime. The special treatment steel bulkheads, the multiple independent fire mains, the extensive compartmentalization, all the design choices that had saved their lives became tangible and comprehensible. In 2005, 60 years after the attack, fewer than 30 survivors attended what would prove to be the final official reunion. They met in Norfolk, Virginia, just a few miles from the Newport News shipyard where their ship had been constructed. The shipyard arranged a special tour for these aging veterans. These men, now in their 80s, walked through the facility where nuclear-powered aircraft carriers were being built using the most advanced technology available. They saw computer-aided design stations where modern naval architects worked on problems similar to those Ferguson had solved with slide rules and drawing boards. Robotic welding equipment had replaced the human welders who had assembled Franklin's hull plating. Advanced composite materials and exotic alloys offered capabilities that Ferguson could never have imagined. But the fundamental philosophy remained unchanged. build ships that survive, design for the worst-case scenario, create redundancy and backup systems. The young shipbuilders working on modern carriers were continuing the tradition Homer Ferguson had established decades earlier. The tools had evolved dramatically, but the mission remained the same. The survivors delivered a simple message to the young workers they met. We're alive today because men like you built our ship correctly 60 years ago. Build these new ships correctly too. Someday, men you'll never meet will owe you their lives just as we owe our lives to your predecessors. It was the fundamental truth of their shared experience. Engineering excellence translated directly into saved lives. Every man who had walked off Franklin alive owed his survival to decisions made in drawing offices and fabrication shops years before the war began. Decisions about steel thickness, bulkhead placement, fire main routing, compartment design. These technical choices had determined who would live and who would die when the crisis came. The chaplain who had fought fires throughout the ship, the engineering officer who had kept the engines running under impossible conditions, the navigator who had organized damage control efforts on the flight deck, all had been enabled by the ship beneath their feet. Without Ferguson's innovations, their personal courage would have been futile. Franklin would have sunk within hours, and 800 survivors would have become 2,500 casualties. Individual heroism required structural support to succeed. The individual stories of Franklin's Medal of Honor recipients illustrate the human dimension of the ship's survival. These men became heroes because their ship gave them the platform and the time necessary to perform heroic acts. Lieutenant Commander Joseph Timothy O'Callaghan received the Medal of Honor, becoming the only chaplain in naval history to be so honored for combat actions. His citation reads in part that Lieutenant Commander O'Callaghan courageously led officers and men in fighting fires and combating damage throughout the ship. He braved dangerous and burning compartments filled with exploding ammunition and threatened by advancing flames to lead rescue parties below decks and save lives trapped in damaged areas. His stout heart, great courage, and cool leadership provided a rallying point for the entire crew during their darkest hours. After the war ended, O'Callaghan returned to his previous position teaching at Holy Cross College in Worcester, Massachusetts. He taught mathematics and physics courses, eventually becoming head of the physics department. He rarely spoke publicly about his Medal of Honor or his experiences aboard Franklin. He preferred to let his wartime service speak for itself while focusing on educating the next generation of students. O'Callaghan died in 1964 at age 62. His autobiography, I Was Chaplain on the Franklin, published in 1956, remains one of the finest and most detailed accounts of the attack and the crew's response to it. Lieutenant Junior Grade Donald Arthur Gary received the Medal of Honor for his actions in the engineering spaces deep within the ship. His citation specifically notes that he organized and led firefighting parties to the hangar deck under extremely dangerous conditions. He entered the number 3 fire room to raise steam in one boiler, restoring power when the ship desperately needed propulsion to survive. His prompt actions in risking his life to help save his ship were of great value in preventing the total loss of the vessel. The citation specifically identifies his rank as Lieutenant Junior Grade and details his critical role in maintaining engineering power when steam and electrical systems had been severely damaged by the explosions. After the war, Gary left naval service and returned to civilian life in Ohio. He worked as an engineer for Ohio Edison, an electric power company, until his retirement many years later. In 1960, he received a letter from a young naval officer asking for advice about damage control procedures and engineering practices. Gary wrote back with detailed technical instructions and added personal observations about system design. Remember that systems don't fail, Gary wrote. People fail. If you've designed your systems with enough redundancy, with enough backup capabilities, with enough alternative paths for critical functions, then when people reach their limits, when they're exhausted and terrified and ready to quit, the ship will carry them through. Build that kind of ship, Gary advised. Design systems that work even when people can't. Gary died in 1977 at age 56, having spent his civilian career applying lessons learned aboard Franklin to peacetime engineering challenges. Commander Stephen Jurica Jr., the navigator who organized flight deck damage control efforts, received the Navy Cross for his actions during and after the attack. His leadership in coordinating rescue efforts and damage control activities was crucial to the ship's survival. After the war, Jurica continued his naval career, eventually retiring with the rank of captain. His experiences aboard Franklin informed his later work in damage control training and procedures development throughout the fleet. He died in 1993 at age 83, having spent his entire adult life in service to the Navy and to the principles of shipboard survival that Franklin had demonstrated so dramatically. Captain Leslie E. Gersh remained a controversial figure long after the attack. His strict disciplinary approach and autocratic command style had made him unpopular with many crew members even before the attack occurred. After the attack, he faced serious allegations that he had accused men who abandoned ship of desertion, despite the fact that many had been ordered to abandon ship by their officers or had jumped overboard to escape certain death from advancing fires. A formal Navy investigation found no evidence of wrongdoing, concluding that in the chaos and confusion of the disaster, communications had broken down completely. Some men had genuinely believed that abandoned ship had been ordered, while others had jumped to save themselves from immediate death. Gersh was promoted to Rear Admiral after the war ended, but the controversy surrounding his actions continued to follow him throughout his remaining naval career and into retirement. He retired from active duty in 1946 and died in 1975, largely forgotten by the general public and remembered primarily for the controversies rather than his role in Franklin's survival. But naval historians studying Franklin's survival noted that his decision to keep the ship moving, to refuse to give up hope, to drive his crew beyond normal human limits, had been validated by Franklin's ultimate survival. Without both the engineering capability to survive massive damage and the command determination to save the ship regardless of cost, Franklin would have been lost with all hands. Both elements were necessary for success. Franklin's post-war fate proved inglorious compared to her dramatic wartime service and survival. After arriving in Brooklyn Navy Yard in April 1945, she remained there for the duration of the war against Japan. Japan surrendered in August 1945 before extensive repairs could begin on Franklin's battle damage. With the war over and no immediate operational need for her services, the Navy decided that the massive repair costs couldn't be justified economically. Franklin was decommissioned on February 17, 1947, and placed in the reserve fleet at Bayonne, New Jersey. She remained in reserve status for nearly 20 years, a ghost ship slowly deteriorating while moored with hundreds of other surplus warships. The Navy redesignated her CVA-13 attack carrier in 1952, reflecting new operational concepts developed during the early Cold War period. In 1959, she was redesignated CVS-13 Anti-Submarine Warfare Carrier as naval aviation missions evolved. Finally, in 1961, she was redesignated AVT-8 Aircraft Transport, indicating that any combat role was no longer considered feasible. These were all paper changes only. Franklin never left the reserve fleet during any of these redesignations. She was too heavily damaged from the March 1945 attack, and the cost of extensive modernization necessary to make her useful for post-war operations was deemed unjustifiable when newer carriers were available for active service. In 1964, Franklin was struck from the Naval Vessel Register, officially ending her career as a United States Navy ship. Her name became available for assignment to new construction if desired. In May 1966, she was sold for scrapping to Peck Iron and Metal Company in Portsmouth, Virginia, for $228,000. This represented a tiny fraction of her original construction cost, but reflected her value only as scrap metal. However, the Navy repossessed Franklin in June 1966 because of an urgent Bureau of Ships requirement for her 4 turbo generators. These generators were needed for installation in other ships still in active service. Finally, on July 27, 1966, Franklin was sold again to Portsmouth Salvage Company in Chesapeake, Virginia, for scrapping operations. All useful equipment had been removed for use elsewhere in the fleet. On August 1, 1966, tugboats began towing Franklin from her berth in the reserve fleet for the final time. As she moved slowly down the channel toward the scrap yard, a Coast Guard cutter passed by in the opposite direction. The cutter rendered honors with 3 short blasts of its whistle, a naval tradition for showing respect to a ship with distinguished service. The cutter's captain, himself a World War II veteran, later explained his decision. "That ship earned honors during the war," he said. "I didn't care what official orders said about her status. She deserved respect for what she had accomplished and for the men who had served aboard her." It was the last salute Franklin would ever receive from active naval vessels. Franklin was systematically cut apart for scrap over the following months at the Virginia facility. Her steel, including the thousands of tons of special treatment steel that had saved her and her crew, was recycled into new construction projects throughout the American economy. Some of that steel, according to Navy legend though not officially confirmed by documentation, went into the construction of USS Enterprise CVN-65, the first nuclear-powered aircraft carrier, which was commissioned in 1961. Enterprise served for 51 years, achieving the longest service life of any aircraft carrier in naval history. When she was finally inactivated in 2012, naval historians noted that her survivability features traced their lineage directly back to Essex-class design principles. Her extensive compartmentalization and redundant systems reflected the same philosophy that Ferguson had pioneered decades earlier. The ship that had refused to die had taught the Navy how to build ships that wouldn't need to prove their toughness the way Franklin had. Today, researchers at the Naval History and Heritage Command in Washington, D.C. can examine War Damage Report number 56, the official analysis of Franklin's damage and subsequent survival. The document contains over 300 pages of detailed technical analysis, photographs, and engineering diagrams. It remains classified as restricted, not because it contains information about modern carriers, but because the damage control techniques it describes remain so effective that the Navy considers them operationally sensitive. Every damage control school in the United States Navy uses Franklin's survival as a primary case study. Students learn how compartmentalization contained damage, how redundant systems maintained functionality, how crew training enabled effective response to catastrophic damage. Every naval architect designing modern combat ships studies how Franklin's structure held together under conditions that should have caused complete structural failure. The lessons learned continue to influence ship design decades later. Every naval officer planning carrier operations understands that their confidence in taking calculated risks, in operating close to enemy shores, in pressing attacks home against defended targets, rests on knowledge that their ship is designed to survive damage that would have sunk earlier vessels. The broader lessons of Franklin's story extend far beyond naval warfare applications. In any field where human lives depend directly on engineering excellence, the same fundamental principles apply throughout. Design for worst-case scenarios, not just normal operating conditions. Build redundancy into every critical system. Use the best materials available, even when they cost significantly more than standard alternatives. Create systems that don't fail catastrophically when damage occurs, that degrade gracefully under stress, that give people time to react and recover from emergencies. Homer Ferguson applied these principles to aircraft carrier design in 1940. They apply equally to modern airliners, to spacecraft, to buildings in earthquake zones, to nuclear power plants, to any human artifact where failure means death or disaster. The attack on Franklin killed 87 men in 30 minutes of concentrated destruction. But the ship's survival saved approximately 1,700 additional lives that would have been lost if she had sunk. That ratio represents more than 20 lives saved for every life lost. This demonstrates the return on investment that superior engineering can provide when human survival is at stake. The expensive steel, the additional compartments, the redundant systems, all cost substantial money and time and effort during the construction phase. But they purchased 1,700 lives during 30 minutes of combat. No one can calculate what those 1,700 men contributed to the world during the decades after the war ended. How many children they raised, how many businesses they built, how many students they taught, how many other lives they touched through their continued existence. The ripples from their survival spread across multiple generations, impossible to quantify precisely, but undeniably real in their cumulative impact on American society and the world. Franklin's story represents the ultimate victory that occurs before battle begins, in drawing offices and shipyards, where engineers and architects make decisions that determine whether men will live or die years in the future when crisis strikes. These decisions lack the visible drama of combat operations. No one receives medals for specifying thicker bulkheads or insisting on redundant fire mains. No one becomes a celebrated hero for choosing superior materials over cheaper alternatives. But these decisions matter as much as courage displayed under fire, perhaps even more, because they enable courage to succeed rather than becoming futile sacrifice. They provide the foundation upon which heroism can build lasting victory. Homer Ferguson never received a Medal of Honor for designing ships that saved thousands of lives throughout the Pacific War. He never appeared in newsreels or history books as a recognized hero of the conflict. His contribution was too technical, too abstract, too far removed from the smoke and fire and drama of battle to capture popular imagination or media attention during or after the war. But the men of Franklin knew what Ferguson had done for them. The 1,700 men who walked off that burning ship alive, who went home to families and futures, who lived full lives because their ship had refused to die in the face of impossible damage. They knew that somewhere in the long chain of decisions leading from initial conception to final construction, someone had made the right choices consistently. Someone had insisted on the extra steel, the additional compartments, the redundant systems that saved them. Someone had believed that men's lives were worth the substantial extra expense involved in superior construction. And on March 19, 1945, off the coast of Japan, those decisions proved more valuable than all the courage and sacrifice and heroism combined. Because courage without proper tools becomes martyrdom. Sacrifice without adequate capability becomes waste. Heroism without structural support becomes tragedy rather than triumph. But when brave men serve in ships built by capable engineers, when sacrifice is enabled by superior design, when heroism is supported by thoughtful planning and execution, then victory becomes not just possible, but probable. Franklin proved this fundamental lesson at terrible cost in human life and suffering, then brought 1,700 witnesses home to testify to its enduring truth throughout their remaining lives. The ship that shouldn't have survived became the ship that proved survival was possible through proper preparation, validating every decision that had gone into her construction and design.